So share the screen, turn this on. Okay. So I'm actually a day ahead, it looks like. Okay, so, but that doesn't mean I'm going to completely slow down. I'm going to, I'm not going to stop, just going to keep going. But otherwise, I had pretty much done with 1.3. So I'll do 1.4. And 1.4 does not even look like that long of a section. Okay, but 1.5 is certainly longer. As you can see, there's a lot of stuff here. Okay, but we'll do as much as we can of 1.4. Okay, so again, coverage for the exam next week is just chapter 1. So you're responsible for everything here. Okay, and you turn that in as homework. Okay, and that's a requirement. There's a 70% requirement. So if you don't turn in the homework, or if you have less than 70% of the homework, I don't grade your test. It will count as a 0. Okay, and again, in my opinion, that should not be that hard, because after all, in class, I end up doing what, 30%, 40%, 50%, maybe even more of the homework. Okay, question about on the schedule, it says buffer day. What is buffer day? It's not a holiday. You just keep going. I just know from experience that sometimes I fall behind, or we lost a day, or like a couple semesters ago, we had to cancel because of the fires or the bad air or whatever, right? So every now and then I build in something called a buffer day, but it's not a holiday. Just keep coming. And in fact, my strategy is if I happen to finish early, I'll just go ahead and get started with chapter 2. But otherwise, quite often, if there's time, I may dedicate the previous day before a test to questions and answers. So maybe if I finish everything in time, I can just let you have the entire Thursday, September the 3rd, for a Q&A session. You can just ask me questions at a whole time in preparation for the Friday test a week from tomorrow, okay? All right, and tomorrow's second quiz, so just like the first quiz, I'll break you up into your breakout rooms, but everybody's responsible for every question from here on out, so you'll be graded individually instead of by group. But while you're within your group, certainly help each other out, say, this is how you do this problem, this is how you do that problem, or whatever, okay? So that's where we are. So I was done with everything I was going to show you with 1.3, and we'll begin 1.4 now, okay? So 1.4, I'll show you the text. We're reviewing the exponential function, exponential functions. And let me just go ahead and show you the book problems for that again, for the benefit of those of you who don't have the book and never going to get it. Okay, so page 53 looks like 1.4. That's the best I can do for the top part. And that's sort of the bottom part. Trying to get a better angle for 19 and 21, but maybe it's not going to happen. Oh well. Okay, so that's that. Then on the next page, top of 54, we have 21, and I think 21 was the last one. If you can't read it, this is the point 1, 6 and 3, 24, 1, 6, 3, 24, and it says f of x equals c b to the x. So find a function f of x equals c b to the x for problem 21. Whoops, 1, 6, and 3, 24. Okay. All right, so some other key pages in the text. So back to 1.4, exponential functions, page number 45. So here's a definition of an exponential function. Okay, f of x equals b to the x. If you can't read it, it's b to the x. B is a positive constant. Okay, so we don't allow b to be negative. And there's actually one number we're not really allowing, it's 1. After all, 1 to the x, 1 raised to anything is 1. So b should be a positive base. So we're never going to have negative bases for exponential functions. And normally we don't allow b to be 1, because if b is 1, that's a little bit too cheap, because 1 raised to anything is 1. Okay? And they give you an example, f of x equals 2 to the x function. Okay, so that's an exponential function. So there's going to be a constant for the base, but a variable floating up here in the exponent. Okay, now be careful. If you flip them around and say x squared, technically x squared is not called an exponential function. Okay, x squared would be like a power function, right? But 2 to the x is an exponential. So the variable is up here on top, and you have a constant base. Okay, so in general, b to the x, b is a positive number, but usually we don't allow it to be 1. Okay, I'm not sure how much you can read of this, but b to the 0 we know is always 1. B to the 0 is 1. And if x is a negative number, then we know b to the negative n is the same as 1 over b to the positive n. B to the negative n equals 1 over b to the n. Okay. Okay, then on page 46, here's a picture of y equals 2 to the x. And exponential functions generally look something like this if you were to plot a whole bunch of points. 2 to the x. So if you plug in 0, you get 1. So exponential functions generally all go through 0, 1. They go like that. The domain is all real numbers. You can plug in anything. For the range, it looks like the range is 0 to infinity, not counting 0. This graph gets really, 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 really close to the x-axis as an asymptote, but doesn't quite touch it. So 2 to the x, like that. Okay, then a nice picture of exponential functions is on page 47. Again, maybe that's the best that I can show you. Okay, so they're giving you all these exponential functions. I'll try to read them for you. Let's see, this one is 1/2 to the x power. This is 1/4 to the x power. 10 to the x, 4 to the x, 2 to the x, 1.5 to the x. Actually, if you can't see the exponent, all the exponents are x, okay? So that's an x, that's an x, that's an x. And here, this is 1/2, 1/4, 10, 4, 2, 1.5. Now, this one, they put 1 to the x, but again, we usually won't consider 1 to the x because 1 raised to anything is 1, so that's kind of a too cheap function. We don't think about it that much. Okay, so you may notice some things that these graphs have in common. They're all positive. So notice they skew the graph, S-K-E-W, skew the graph. They don't dedicate any space in the third and fourth quadrants because there's nothing down there, right? So the range for all of these is from 0 to infinity. They all go through the same point. Can you see what their point of intersection is? It's 0, 1, which makes sense because for any of these, no matter what the base is, if the exponent is 0, we know that anything to the 0 power is always going to be 1. So all of these touch 0, 1. They all touch here. And you can see they go like that and like that. Okay. Now, it looks like if the base is less than 1, like 1/2 and 1/4, you've got a decreasing function. That's always going to be true. If the base is bigger than 1, you have an increasing function, like 1.5, 2, 4, 10. And also, as you might expect, the bigger the base, the sharper the graph is, right? So if you notice the progression, 1.5 to the x, and then 2 to the x goes up faster, and 4 to the x is even faster, and 10 to the x is even steeper still. But then for these where the base is less than 1, like 1/2 to the x, 1/4 to the x, it looks like they're falling. They go like so instead. Okay, so now in general, let me show you this. I'm still on page 47, those of you following along in the text with me. And like I said, we're hardly going to talk about this at all. Y equals 1 to the x. well, 1 to the x is 1, so you just have that. So that's kind of too cheap. Okay, so the two key ones that you want to notice are these two. So based on what we said, y equals b to the x if b is between 0 and 1. So less than 1, but still positive. We're not going to consider negative bases. Then the graph is going to be falling. Okay? So on this side, it shoots up to infinity, but on this side, it gets really, 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 really close to y equals 0 as an asymptote. Okay, and then here, y equals b to the x if the base is bigger than 1. Like these guys here, 1.5, 2, 4, 10, or whatever. Okay, it's going to be an increasing function. Notice they still go through 0, 1, 0, 1, 0, 1, 0, 1. All of these touch 0, 1, but it's going to be an increasing function if the base is bigger than 1. Okay, so then on this side, it shoots up toward infinity, and on this side, it gets really, 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 really close to 0. It approaches the x-axis as an asymptote. Okay. All right, then we have some laws of exponents. You remember these from your algebra, hopefully. I will read them in case you can't see them. You should already be familiar with them. It says b to the x plus y, b to the x plus y equals b to the x times b to the y. Okay. So to multiply these, you add the exponents. We saw that before. This says b to the x minus y. That's b to the x over b to the y. Right? B to the x over b to the y, b to the x minus y. This one, you have a power followed by another power, b to the x to the y. You just multiply the powers, b to the x, y. And then finally, ab to the x power, a more complicated base. You can distribute that x onto the a and the b. So it's a to the x, b to the x. Is that right? Okay. I'll show you this. So it's a good idea to have a general idea of the exponential function, that you should be able to say, oh yeah, exponential functions look like this if the base is bigger than 1, or they go like this if the base is smaller than 1. And then you should be okay with transformation. Okay, take this and, you know, reflect it, move it up, move it down, move it left, right, and so on. So I'll just show you a quick example of that before we look at some of the homework problems. Sketch the graph of y equals 3 minus 2 to the x. 3 minus 2 to the x. Okay, and they do that on the next page. So you start off with 2 to the x. Okay, so we have 2 to the x. And then minus 2 to the x. That's like negative 2 to the x. So you recall what happens to the opposite of f of x. It just reflects across the x-axis. So pretend you take the graph now, and my ruler here is a mirror. It reflects down, so now it looks like this. Right? So this is the graph of negative 2 to the x. And then 3 minus 2 to the x, that means just add 3. So that means you take this graph and shove it up 3 units. Go 3 units up. Easiest way to do that is take a nice point. So this was the point 0, 1. This is the point 0, negative 1. And now if I just move it up 3 units, that would be 0, 2. So it comes way up here. And the asymptote used to be the x-axis, which is like y equals 0. Okay, so that moves up 3 units. So y equals 0, go up 1, 2, 3. And now the asymptote is y equals 3. So here's a quick and dirty sketch of y equals 3 minus 2 to the x. So you can start off with 2 to the x, your basic function, and then negative 2 to the x flips it down here, and then just move the whole thing 3 units up. So see how it's got negative 1 here, right? So 0, comma, negative 1, move it up 3 units to 0, comma, 2. And yes, even the asymptote moves up 3 units. So the asymptote used to be the x-axis, which is like y equals 0, right? So move it up 3 units, and now it's up here at y equals 3. Okay, the domain is all real numbers. This thing keeps going as far as you want to the left. It keeps going as far as you want to the right. For the range, so you see the domain is all real numbers, the funny looking R. The range, you can go infinitely far down, so you can go as far down as you want, but there's a limit as to how high you can go. So you can't get past 3, and you don't actually reach 3 either. So we write it like this for the range, parenthesis negative infinity, because it shoots all the way down, up to 3 and a parenthesis. So you don't actually reach 3. If you reach 3, there's a bracket, right? But you don't. So parenthesis means 3 is not there, but 2.9999999 is there. Okay. Okay, that's about it for that. Just want to mention quickly, there is something called the number E. Have you heard of the number E before? Okay, so E is about 2.7, 2.71828 or something like that. Okay, so you'll be using the number E a lot in calculus later on, right? So we want you to know about this E. I know it's kind of weird to say, what's so good about the number E? When we get to the calculus formally, we're going to see E a lot. In fact, there are going to be some instances where we like the number E better than any other number. We don't like other numbers besides E. But for now, it's like 2.7, 2.718, something like that. Okay, its still shape is going to be something like that. Okay, so here's 2 to the x, here's 3 to the x. They're trying to show you here e to the x. There's e to the x. It's like 2.718. Well, here we go. Got e is about 2.71828. Okay, and I'll just mention something quickly about the calculator. You don't need your calculator right now, but you'll want to find it eventually. So on my calculator, usually e to the x is paired with ln. Okay, so on your calculator, if you have a calculator, you can look at it, but I'm sure you've seen it before. Usually there's an ln, and right above it is e to the x. So that's how you would get, e to some power. So if you actually want to see the number e, what you could do is do, let's say, e to the first power. Okay, so on my calculator, I don't know if you can see it. See if I can angle it right. Well, you can kind of see. I typed in e to the 1, and it's got 2.71828. Sorry if you can't see it, but I did e to the first power, 2.718281828, something like that, for e. Okay. All right, so that was introduction, and now we're ready to start some of the 1.4 problems. We just have 1 to 21 odd. So here we go. Okay, so at this point, I'll lose the book and go straight to my notes that I did before. Okay, so 1a, 4 to the negative third over 2 to the negative 8. Okay, and you might recall for negative exponents, if you have a negative exponent on top, you're allowed to bring it down and change it to a positive. So 4 to the negative 3 on top becomes 4 to the positive 3 in the bottom. And similarly from algebra, if you have a negative exponent on the bottom, you're allowed to bring it up. So that's what I meant by the arrow there. 2 to the negative 8 on the bottom can become 2 to the positive 8 on top. Okay, now at this stage, yes, you could punch it into your calculator, but I'm going to try to show you a little bit of a trick. Okay, since this is base 2, I'm going to show you that you can change this to base 2. And you can do this trick even if you don't have a calculator, frankly. So 4 is equal to 2 squared, right? So let me cover the exponent of 3. All I'm doing is 4 is equal to 2 squared. Do you agree with that? So here, the bottom is still 4 cubed. Do you agree? This is equal to this. Here's 4 cubed. Here's 4, 2 squared, cubed. So it's still 4 cubed. And then I have a property of exponents that says if I have something like this, if I have a power followed by another power, I can just multiply these powers. So that becomes 2 to the 6th power. So I have 2 to the 8th over 2 to the 6th. And when it's like that, the rule is that I can subtract the exponents. 8 minus 6 is 2. So I have 2 squared is equal to 4. So my answer is 4. And notice I never needed to use my calculator for that. I didn't have to punch out what's that or whatever. I did a little trick like this and I got 4. Now, do I have to do that on a test? You say, no. If you just want to punch it in the calculator, you could. But every now and then, I'm supposed to show you little tricks like that, I guess. Way to say it. Okay, question B. Looks like this. All they want me to do is write it as an exponent. So 1 over the cube root of x to the 4th. Okay, so you might recall to go from here to here, you write a fraction. The top is the power, the bottom is the root. So it's power over root, that's x to the 4/3, right? So power divided by root, 4 over 3. Okay, a memory trick that I often give is think of the root of a tree or the root of a plant, right? It's down, so the root is further down, 4 over 3. Okay. So if you had to memorize this, I would put power over root, but frankly for you guys, I'm not making you memorize it anyway because you can put it in a cheat sheet if you wish, although you may want to save your cheat sheet for other stuff. Okay, so anyway, again, power on top, root on the bottom. Okay, then problem 3b, temporarily cover that up. 6y cubed raised to the 4th power over 2y to the 5th. Okay, so right now there's nothing to do on the bottom. The top, you distribute the 4. The 4 goes here, the 4 goes here. So I have 6 to the 4th power, and then y cubed to the 4th power. And do you remember what I do in this situation? If you have a power, then you immediately have another power. We multiply them. Okay, and this one, just punch in your calculator. 6 to the 4th, 6 times 6 times 6 times 6, divide that by 2. It comes out to be 648. Just punch it in your machine. And then what's the rule over here? Y to the 12 minus 5 equals 7. So there we go. 648, y to the 7th power. And that's it. Okay, then let's see, problems 7 and 9 are very similar. Graph these on a common screen. So I think I did for you 9. Okay, so 9, you have 3 to the x, 10 to the x, 1/3 to the x, 1/10 to the x. Okay, so I have them over here. Okay, 3 to the x, 10 to the x, 1/3 to the x, 1/10 to the x. Okay, so before going on, I'll ask you a question. Which one of these are going to be increasing and which ones are going to be decreasing and why? 3 to the x, 10 to the x, 1/3 to the x, 1/10 to the x. Which ones are increasing? Which ones are decreasing? Okay, these two are increasing. These two are decreasing. Okay, so if the exponent is bigger than 1, it's going to increase. If the exponent is smaller than 1, it's going to decrease. Okay, so you see I have 2 that are going up and 2 that are going down, but I'm going to quickly cover it. Okay, so now let's just consider these two. Okay, so 3 to the x, 10 to the x. So which is going to shoot up steeper? 10 to the x is going to be steeper. I mean, stop and think about it. Even when I plug in 1, right? If I plug in 1, this one's 3, but this one's already up at 10. So this one's winning, quote unquote. And it even gets more pronounced when I plug in 2. If you plug in 2 here, you get 9. If you plug in 2, that's 100. So it's shot way past it. Okay, so for 3 to the x and 10 to the x, so 3 to the x is below 10 to the x on this side, but it turns out on this side they switch rows. Okay, so I've drawn, I'm not sure if you can see it, but I got the green one. The green one is 3 to the x. Okay, so I'll trace it for you. This one is 3 to the x. This one in blue is 10 to the x. So yes, on this side, 3 to the x is below 10 to the x. But on the negative side, they actually reverse. So if I reverse it, 3 to the x is above 10 to the x on this side. And if you stop and think about it, that actually makes sense. Okay, because if on this side it surpasses it, and they all touch 0, 1, right? They all touch 0, 1. So that must mean on this side, 3 to the x is above. Okay, but 10 to the x being steeper, it gets steeper, 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 then they touch, and then after that, it shoots past it. Okay, and then the same thing for, I guess, 1/3 to the x and 1/10 to the x. So how do I graph these relative to each other? Okay, and again, easy way to think of it is, okay, all 4 of these go through the same point. What was that same point that they all go through? They all go through 0, 1. Because if you put a 0 here, or here, or here, or here, it doesn't matter, they're all going to be 1, right? So which one's above and which one's below? Okay, well, an easy way to think of it is to plug in 1. If you plug in 1, this is 1/3. And if you plug in 1, this is 1/10, right? So which is higher, 1/3 or 1/10? 1/3 is bigger, right? So that means 1/3 to the x is above 1/10 to the x. Okay, I've got this one, I guess, in blue, and the red one is 1/10 to the x. Okay, so that means on the other side they switch. So let's see, on this side the red one is lower, which means on this side the red one is higher, and I guess the black one is lower. Okay, so after the 2 graphs pass 0, 1, they switch. So whatever was lower on this side was higher on this side. So I don't know if you can see the red one, but I'll trace it. This one is 1/3 to the x. Oops, I'm sorry. This one is 1/3 to the x. This is higher than 1/10 to the x on this side. So on this side, 1/10 to the x, the red one, is higher, and 1/3 to the x is the lower one. Okay. Okay, so very quickly, some of these. Make a rough sketch. Don't use a calculator. Don't plot points. Just start with the basic graph and do the transformations. Okay. So number 11, please. 4 to the x minus 1. All right, so you start with your basic 4 to the x, goes through 0, 1. This side it shoots up to infinity, this side goes to 0. And what's the effect of the minus 1? It just drops the graph 1 unit. Okay. So this point used to be 0, 1. If I drop it 1 unit, it goes through the origin. And it go like that. Sorry, if you hear a funny noise, that's my computer making a whirring noise. I don't know why it does that. But fortunately, I'm getting a new computer tomorrow after class, so I just need this computer to last until after class tomorrow. And then I'll get a new one, hopefully. Okay, the asymptote changed also. The asymptote used to be the x-axis, which is y equals 0. Shove it down 1. So y equals -1 is my new asymptote. Okay, so asymptote, A-S-Y-M-P-T-O-T-E. It's a line that the graph gets really, really close to. Okay, then I wanted to show you 15. y equals 1 minus a half e to the negative x. Okay, so there's a lot of things going on here. All right, so first I start with e to the x. Standard exponential function goes through 0, 1. This one is e to the x. E is like 2.71828, something like that. Okay, what does e to the negative x do? So if you replace x with negative x, you might recall you get the reflection across the y-axis. Okay, so I know it's in two pieces, but this piece right here reflects over to there, and this one reflects to there. So e to the negative x looks like this. Okay, now what else do I have over here? So what's all this stuff, you might say? Negative a half e to the negative x. Okay, so I know the negative is going to reflect across the x-axis, so it's going to come down instead, and it's only half as big. So ignore the 1 right now. Okay, so I'm trying to illustrate that right over here. So if I just take this graph, e to the negative x, reflect across the x-axis, I get this one in red, that's negative e to the negative x. So this one and this one are mirror images of each other, reflection across the x-axis. So this is e to the negative x, this is negative e to the negative x, and now negative a half means it doesn't go as far down, so I've got it like that now. Okay, so now the green graph is negative a half e to the negative x. So notice I'm showing you the progression, and you should do likewise for me on homework, quizzes, tests. Okay, don't just give me the answer. Start with a basic function like e to the x. Okay, all right, then e to the negative x goes like that, and then negative e to the negative x goes like that, and then negative a half e to negative x goes like that. So this was the point 0, negative 1. Okay, 0, 1. If you reflect across the x-axis, 0, negative 1. But it's only going to be half as high, so 0, negative a half is what I have now. And finally, at long last, okay, I have this one. I add 1. So the whole thing goes up 1 unit. And this time I decided to draw a brand new graph because the picture is getting cluttered up after a while. So how do I graph that? Well, just take a nice point like this, 0, negative a half, bring it up 1 unit. So where will I end up if I take 0, negative a half, bring it up 1 unit? 1 unit higher is 0, positive a half. Negative a half plus 1 is positive a half. So this is 0, comma 1 half. And I just take the same basic shape as that green one. And that's what I got now. So it goes something like that. So y equals 1 minus a half e to the negative x. Looks like that. Okay, yeah, I know there's a lot of stuff there. Okay, the next one I was going to show you was 17, and maybe that was about it. Okay, so 17, please. Yeah, no, it's hard to read. I'll say it, and again, if you have the book, just go with it. Starting with the graph of e to the x, write the equation of the graph that results in all of these things. Okay, so I'll try to write it for you also, so bear with me. Okay, so your basic function is e to the x. Let me write y equals e to the x. It looks generally like that. It's increasing, 0, 1. On this side, it shoots up. On this side, it goes towards 0. Okay, first one says 2 units down. So what is it going to be for 2 units down? It's e to the x minus 2. So y equals e to the x minus 2. That's 2 units down. Two units to the right. How do I go 2 units to the right? Okay, that's where you replace x with x minus 2 in parentheses. And unfortunately, that's counterintuitive. Okay, so it looks like this. And you have to watch out. Here, the minus 2 is part of the exponent, but not here. This is e to the x, and then separately minus 2. That minus 2 is not floating up there. Here it is floating up there. Okay. I know what I'll do. So this is 2 to the right, 2 down, since I have them separated. So this is the one where it's 2 down. This is 2 to the right. C. Reflect about the x-axis. Take a graph and reflect it about the x-axis. Well, we actually did that over here, right? E to the x, reflect about the, we did it about the x-axis and y-axis. Okay, so if we reflect about the x-axis, it comes down to here. So it's negative the function. So y equals negative e to the x. Reflect about x-axis. Negative e to the x. D. Reflect about the y-axis. Same thing, we did that over here. Here's e to the x. If we reflected about the y-axis, then we got e to the negative x. Okay, so that's going to be e to the negative x. Reflect about y-axis. And finally, E, it says reflect about the x-axis and then about the y-axis. So you're reflecting both of them. So you basically have both negatives, that's all. So y equals negative e to the negative x. So you reflect about both axes. So reflect about both axes. AXES is the plural. One axis, two axes. Okay. So if you go about the x-axis and then you go about the y-axis, you're really just combining both of these, right? They're both there. So minus, minus. And there we go. All right, and that'll do it for today, folks. So I will stop and turn off